from Shillong, Northeast, from everywhere, from Pan
Ah,
India,
so
they will
we'll,
be across the country. Yeah.
yeah, we'll do it in English primarily, but I'll be able to answer some questions in Hindi if you think that there are specific terms that
Mm-hmm.
we should be doing in Hindi.
Yeah.
उसके लिए मैं switch कर सकता हूँ कुछ देर के लिए.
Yes, because children includes government schools. Children are also there,
Right.
so that I want that थोड़ा सा mix अगर आप रखेंगे,
हाँ ठीक है,
will be
कर
good.
सकते हैं. पर
Thank
वही
you.
मतलब अगर कंटिन्यूअस इंग्लिश हो रहा हो तो फिर आप बता सकते हैं कि ये इसको हिंदी में कैसा कहेंगे या ऐसे कुछ.
No, no, sir. It's totally up to you. But I want the session to be more joyful for all the children. So that is why, so everybody should understand. So that is why I'm saying it's okay. Because mostly Navodaya children, they are from CBSE schools, but government schools are also part of this program. So that is why I want some consideration for them also. We have with us Dr. D.K. Modi sir also. D.K. Modi sir is senior consultant for the Vigyan Jyoti program. Justi is from Team American India Foundation, and American India Foundation is the implementing partner of IBM. IBM is our CSR partner for this Vigyan Jyoti program.
Right.
We have 250 schools at present wherein this Vigyan Jyoti program is going on, sir. And it is an initiative of Department of Science and Technology, wherein girls children are being supported. These girl children are from class 9 and class 12. So basically, to motivate these students to pursue STEM career in their fields, this program has been started, and there are many activities which are going under this program. Role model interaction is one of them. Apart from this, we are conducting some experiential learning workshops and some knowledge partner visits. All the institutes like IITs, ICER, NITs, CSIR institutes, these all are the knowledge partners wherein students go and experience the lab experience, visit, interact with scientists, and also we are having academic support classes towards preparation of competitive examination. And apart from this, monetary benefits are also being provided to the students, where in class 12, 11, 12 students receive 1,000 rupees scholarship per month for 12 months, and also resource material in the form of books and some other reference books, competitive books, that has also been provided to class 12 students. So all in all, it is a mix and match of various activities, and through which government is supporting these girl students to do better in their career in STEM fields.
Ma'am, we are live stream. Are we good to go?
I think just we can give 5 minutes more. We can wait for 5 minutes, so that some more schools join.
Sure, ma'am.
Yeah.
Can I try sharing my screen meanwhile?
Yes, sir. You can just try.
I think I don't have permission, so maybe the host needs to give permission.
So please try it again. And also I'll give you hosting rights.
Okay, can you see my screen?
Yes, sir, it is visible.
And can you see it full screen now? I guess it's loading.
It's loading, yeah.
Okay.
Yes, sir. Could you change the slide once just to see if
Sorry?
Sir, could you change the slide once?
Oh, meaning go to the next slide?
Yeah.
Okay, let's see.
Yes, yes, sir, it is working.
Yeah, okay, that's good. Well, shall I stop sharing for now?
Sure, sir.
Because then if you want to do any introduction, we can do that. And yeah, okay, that's good. Well, shall I stop sharing for now?
Sure, sir.
Because then if you want to do any introduction, we can do that. And yeah, okay, that's good. Well, shall I stop sharing for now?
Sure, sir. It is a request to all the teachers to keep yourself muted. It is a request to all the teachers to keep yourself muted. Mandeep, could you figure out how this audio is being repeated?
You were hearing an echo or something?
Yeah, I mean, after a few seconds, I'm hearing back what has already happened.
Yes.
I think here
Mandeep,
things
could you
seem
figure out
fine.
how this
Here we
audio
go.
is being repeated? Is it from my end only?
No, I can also hear.
You were hearing an. Yes,
You
yes.
are muted, Justin.
I'm actually not being able to figure out what is the source of the echo. Mandeep, most probably it will happen again now that I'm speaking. Could you just check in the participants list if there is anybody who's unmuted and from there the echo is coming? I'm actually not being able to figure out what is the source of the echo. Mandeep, most probably it will happen again.
Justy, do you have your YouTube open? The voice is coming from there. It happens with
Yes,
me. So
actually,
just,
my YouTube was opened.
yeah, it happens with me.
Yes.
You
yes.
mute your YouTube.
Yeah, I have closed it. I did not realize that it was opened. Anyway, thank you.
I think we shall start, sir.
Ashish sir, Modi sir, shall we start?
Better to start now, Justy.
Okay, sir. Yeah. Good morning, everyone. Welcome back to yet another inspiring interaction session with India's Science Geniuses, brought to you by the Vigyan Jyoti program. And today we have none other than Dr. Ashish Mahabal leading the lecture for us. I know all the students might be excited to know more about the speaker. So without taking any further ado, I invite Dr. D.K. Modi, the Senior Consultant of Vigyan Jyoti program, to deliver the welcome address and also to introduce the speaker to us. Over to you, Modi sir.
Thank you, Justy. Thank you, Justy. On behalf of Department of Science and Technology and Navodaya Vidyalaya Samiti, I welcome you all to the 6th session of lecture series, Interactions with India's Science Genius. The series is one of the unique activities under role model interaction conducted for all the Vigyan Jyoti scholars. This initiative was inspired by the book India's Science Genius, written by Dr. Archana Sharma, scientist at CERN, Geneva. The first lecture was delivered in December 22 by Dr. Archana Sharma herself, and subsequently lectures have invited the other eminent scientists featured in her book. The series is conducted by the Vigyan Jyoti team at NVS headquarters and is facilitated by IBM's partner American India Foundations. To deliver today's role model session, we are extremely privileged to have Dr. Ashish Mahabal from California Institute of Technology, US, who has joined us from California. May I now have the pleasure of introducing him, the audience. Dr. Ashish Mahabal is an astronomer and lead computational and data scientist at the California Institute of Technology, USA. Dr. Mahabal is also contingent faculty at the Inter-University Center for Astronomy and Astrophysics, Pune. His interests include large surveys, classification, deep learning, and methodology transfer to other complex data fields like medicine. He leads the machine learning for the Scully Transcend facility, a large sky survey covering the entire sky every few nights. He also works with data science group at the Jet Propulsion Laboratory and is part of the Consortium for Molecular Characterization of Screen Detector LISA and the Early Detection Research Network for Cancer. The exploration of space and the resulting science that human has managed over the last several decades has been limited by onboarding, processing, and possible data transfer to Earth. The recent development in process technology combined with machine learning advances has opted by many new possibilities for extended scientific mission as well as possible ways to take advantages of accidental observations. Implementation of such technologies has already taken place near Earth. Last year, in Institutes for Space Studies at Caltech studies how best to take advantages of such larger data taking and processing capabilities. We can now incorporate on individual spacecraft and interest work components like landers, rovers, and orbiters. Dr. Mehra, we welcome you to the session and all of us, including the students, are excited to learn from you about your work and how to use Zarath astronomy app developed by your team. As we speak, it is past 9:30 a.m. in Indian time of 18th October here in India. And I believe it is past 9 p.m. on 17 October as per your local time of California. Dr. Mahabal, as you would be aware, the program Vigyan Jyoti is an initiative of Government of India's Department of Science and Technology, being implemented in 250 knowledge centers at JNBs and aiming to inspire the meritorious girls students from class 10 to 12 standard to pursue a career in a STEM field. Once again, I take this opportunity to welcome all of you to enjoy this session. I do hope these interactions will be very much fruitful and memorable for all the VJ scholars. I don't want to take much of your time because all the VJ scholars are anxiously waiting to listen to you. Over to team AIF. Thank you. Thank you very much.
Thank you so much, Modi sir, for the welcome address and for introducing the speaker to us. So students, now I hope you all have your tablets or phones with you and you have installed the Zarath app, because now is the most exciting part of this entire session, I feel, which is exploring the sky through a gaming app, which is like Pokemon Go, if you all have, played it ever. So over to you, Ashish Mahabal, sir. We are most honored to have you among us. Yeah, we can start with the session now.
Thank you for the kind introduction. And I'll start by sharing my screen. Okay, let me know once you start seeing it. Can you see it? Okay, yes. Perfect. Okay, so yes, my name is Ashish Mahabal. I work with Caltech and at IUCAA, and I'm going to talk to you today about transient astronomy and ZART, and you'll get to know what these terms are in a little bit. Feel free to stop me in between or ask questions. We'll also have question answer time towards the end. So this is going to be the broad outline that I'll be talking to you. I'll first mention how astronomy has been changing. Then I'll talk about sky surveys, how we observe the entire sky multiple times. Then I'll go into some details about few types of objects, because if you look at the sky, you see many stars, and at the first look, it seems all stars are like each other, but there are very big differences in them. And with the eye, you cannot make out those differences, but as you start using telescopes, you can make these differences out. And it is the understanding, the knowledge of these sources that really helps us understand about our universe, about our solar system, everything around us, and also our own, how we came about, how we were formed. Are there other planets which may have life and things related to that? One important bit I will touch upon is about data sparsity. So if we had infinite data, then we'd learn about everything really quickly, but we don't have infinite data. We have limited resources, and within those limited resources, we try to collect the data that we have, and still with the limited data, we can learn about a lot of things, and I'll tell you how to do that. And then I'll come to the Zwicky Transient Facility and transients in particular. So Zwicky Transient Facility is a sky survey, which I am a part of. I lead the machine learning for that. And transients are types of objects that change in brightness rapidly. So you'll learn a little bit of it. And to understand what they are, we need to understand what light curves are and what cutouts are. So I'll spend a little bit of time on that. And then I'll come to ZART, which is the most exciting part, as Justin said just now. So how astronomy is changing. So in the old times, the only thing that we could see that were different from the stars were the planets, because the planets moved on the background of the stars. Because planets belong to our solar system, we can, if you keep on looking at the stars day after day, night after night, you'll see that the planets are the ones whose relative positions change. And that was the only knowledge that we had. And that initially helped us understand what our solar system is. It also led to many things where people believe that planets may be affecting our lives. Planets do not affect our lives. They're really far away and they're just going along their path. So that doesn't happen. And those are the kinds of things that we slowly learned. And then we learned about different kinds of stars. We figured out that there are galaxies also within these stars. And these galaxies are like island universes. Just like our own galaxy is the Milky Way galaxy, which has 100 billion stars. So there are other galaxies which have hundreds of billions of stars, and they're far, far away, and they're really tiny. And then quasars were found. These were quasi-stellar objects. So these are like the centers of the galaxies, but so bright that they outshine all 100 billion stars. And then we started going from only a few observations to many, because there were few telescopes, the resources were not enough. We could observe each object maybe once or twice in several years. Whereas now with sky surveys, we can observe the entire sky in 2 to 3 days. And we keep on doing that again and again. So the sky survey that I started working on when I came to Caltech, it took 15 years to do just the north sky, one image in 3 filters. So again, 15 years for one sky survey. And now we do one sky survey in 3 days. So you can imagine how the technology has changed, how rapidly things have happened. Earlier, we had to use photographic plates, like the old cameras that used to be there. Maybe some of you have seen that, but maybe most of you don't have. There used to be this roll and you turned it and you exposed it, and then you had to take it to a dark room to develop it. So even astronomy was like that. We had photographic plates. We put them on the telescopes and observe the night sky with them. But then we went to CCDs, charge coupled devices. And it's exactly like how there are cameras in your cell phones, in your smartphones. You directly expose it and you get the image immediately, right? And then there's also a little bit of machine learning and so on, but we won't go into those details. Okay, so what are sky surveys? There are many, many sky surveys that are possible, and they use different technologies. But the main thing to remember is that with sky surveys, you can do hundreds to thousands of observations of the same object, of the same star, of the same galaxy, and so on. And how many sources are there in the sky? As you have bigger and bigger telescopes, you can look at billions of sources. With your naked eye, if you go to a very dark spot, say away from your city, away from your town, and look at the sky, at a time you cannot see more than a few thousand sources. So with the eye, you can see only several thousand sources. But the eye has a very small diameter. Our telescopes have much larger diameters. Not just that, with the eye, you can see for only 1/25th of a second, the persistence of vision. Whereas with a telescope, we can keep the iris open for a long time, collecting all the photons, say for 30 seconds, even half an hour on some telescopes. So all those photons together allow us to see much fainter objects. So we can see hundreds to thousands of observations. और मुझे बताया गया था कि थोड़ा हिंदी में भी बोले, तो थोड़ा सा उसमें भी बता देता हूँ। आजकल हम जो स्काई सर्वेस कर पाते हैं, उसके कारण हम पहले आंखों से देख सकते थे और अभी भी आंखों से देख सकते हैं, उससे से कई गुना अधिक सारे गैलेक्सीज देख सकते हैं। और उनकी हम कई बार ऑब्जर्वेशंस इसलिए लेते हैं ताकि हमको पता चले कि उनमें चेंजेस कैसे हो रहे हैं। So understanding changes is the main thing that we need to do with these sky surveys. So that's what we are after. So we'll take a look at a few types of sources: tidal disruption events, active galactic nuclei, pulsating stars, binary stars. There are many, many different possibilities. And we'll watch short videos to understand what some of these are. So for instance, here is a tidal disruption event. When a star comes close to a black hole, it gets ripped apart by the black hole. And then it suddenly becomes bright. And we can see that brightness. So here, the bright spot in the center was the black hole. And then a star came close to it. And because of the gravitational force of the black hole, it was just torn apart. And we can see the debris of that. Then here is another example. This example is an active galactic nucleus. Again, at the center of the galaxy, it is really bright. It outshines the rest of the galaxy. But here, one interesting thing is when you look at it from different directions, it looks somewhat different. And so, for instance, just like what would happen is that if you have something that is edge on, it would look different, whereas if you turned it, it would look different. Think about a frisbee. If you put the frisbee in the same plane as your eye, it would look like a disc or a line. But if you turned it around, then it will look like an entire dish or a frisbee proper. So similarly, with this active galactic nuclei, they're bright, but they're surrounded by other stars, dusty material, and so on. And depending on where we are looking at it from, it looks different to us. So here, for instance, we are changing direction. And as we change direction, even if the mechanism is the same, at the center of the galaxy is a huge jet sending out energy. And if you are looking at it from one angle, it looks like what is called a blazar. If you look at it from another angle, it's called a quasar or a Seyfert-2 galaxy, etc. So all these changing things are there in the sky. And if we look multiple times with the sky surveys, then we start seeing those. Then there are other things also that are changing. I'm trying to go to the next page and didn't do that. Okay, yeah, here. So this is a Cepheid star or RR Lyrae star. These are pulsating variables. Now, these are not stars that are changing brightness due to something else, but they are becoming smaller and bigger. And that is what is caught in this case. So the
Cepheid stars undergo periodic changes in luminosity. Delta Cephei is among the closest stars of this type of variable.
It's pulsating like
only
this,
Polaris
changing, and that is why its brightness is changing.
Most stars have some variability in their luminosity.
And then what we do is
Even
that we also plot the brightness of that object as a function of time. So if you observe it now, it's bright, then it's faint, then it's bright, then it's faint. And so what we can do on the x-axis, we can have this time, and then we get something like this. It becomes brighter, fainter, and it's timed, it's periodic. So that's what we are trying to understand. Then we'll look at a fourth case. This is a case of a binary eclipsing star. So just like there are solar and lunar eclipses, what can happen is that there can be stars that are going around each other.
Greater percentage of systems are
I'll just leave this on for half a
meaning
minute.
that they are systems containing 2 or more stars, and in particular, binary star systems, which specifically contain 2 stars, are exceptionally common. When we can see both of the stars, they are called visual binaries, and if the plane of their orbit happens to coincide with our line of sight,
this is the time axis that I had mentioned, and the brightness is on the y-axis, right? And so, okay, it seemed to have skipped.
Solar system has just one star, the sun. But this is actually a bit uncommon in the galaxy. A greater percentage of systems are multiple star systems, meaning that they are called visual binaries. And if the plane of their orbit happens to coincide with our line of sight, such that they pass in front of.
Okay, so again, it's somehow skipping. So let's try once more. Somehow not.
Solar system has just one star, the sun. Stars, they are called visual binary, pass in front of each other.
Yeah.
They are called eclipsing binaries. This situation allows us to gather important information about.
So you can see that they're going around each other. When one eclipses the other, brightness decreases. When the other eclipses the first, brightness decreases. And so the brightness is decreasing, increasing, flat, decreasing, increasing again, and so on.
The smaller star passes in front of
so
the larger.
These are the different kinds of variability that you can see. And as I mentioned earlier, if we can continuously keep looking at this object, then we can easily see how the brightness changes. It reduces, goes up, stays flat, comes back, and so on, right? But the data that we look at is sparse. Do you remember the story of several blind people and an elephant? The blind people look at some part of the elephant and they think that the elephant is like that. With astronomy also, something like that can happen. So here is an image of something that is called a dwarf nova. And here you can see that a small region is magnified, another small region is magnified, and a third small region is magnified. And you can see that they look so different from each other. And yet the object is the same. It is the same object which we are looking at different times. So if someone was to look at it only this portion, and someone else were to look at only this portion, they may think that these are 2 completely different objects. But that is not true. And that's what we need to understand. So this sparsity is somewhat like what we have in, say, you're gone on a jungle safari. You want to find out animals. And so what you do, you look around, try to spot an animal, then you look somewhere else, try to spot another animal, and things like that. But suppose instead of being able to look for the animals all the time, suppose you had to blink many times, not just blink, but maybe you had to keep your eye open for 1 second and close it for 5 seconds. Then look somewhere else, look for 1 second, close for 5 seconds. You're going to miss most animals, or sometimes you're just going to see an animal quickly go by, not the entire activity of the animal. In astronomy, exactly that's what happens, right? So we are not looking continuously at the sky. So I look at one part of the sky for 30 seconds tonight. Then 2 nights later, I come back and look at it again for 30 seconds. So in that time, if I catch the variability of an object, I can determine what it is, but many times I cannot. So even with this sparse data, we need to make sense of the things that we are finding. So for the jungle thing, let me again mention that in Hindi. अगर हमें कुछ एनिमल्स देखने हो इसलिए हम जंगल चले गए और वहां पर हम कंटिन्यूअसली वहां देखने के बजाय अगर आंखें थोड़ी देर बंद रखते हैं, फिर आंखें खोलते हैं, फिर बंद कर देते हैं आंखें थोड़ी देर, फिर बिल्कुल कम देर के लिए आंखें खोलते हैं, और ऐसे अगर एनिमल्स को ढूंढते रहे हम, तो ज्यादा एनिमल्स हमको दिखने नहीं वाले. पहले तो हमने वहां आंख बंद कर दी तो हमको कोई आके खा जाएगा, पर अगर खाता नहीं है तो भी ज्यादा एनिमल्स हमको दिख नहीं पाएंगे. एस्ट्रोनॉमी में भी वैसे ही होता है. हमारे टेलीस्कोप्स जो होते हैं, हरदम हम एक जगह पे नहीं देख सकते उससे. तो अगर कहीं हम आज 30 सेकंड देख लिया, फिर 2 दिन बाद फिर से 30 सेकंडों के लिए देख लिया, फिर 2 दिन बाद 30 सेकंडों के देख लिया। इतना कम टाइम हर जगह पे मिलता है क्योंकि आकाश बड़ा है और टेलीस्कोप को सब तरफ घुमाना होता है, तो उसके कारण हमको लिमिटेड इंफॉर्मेशन होती है और उस लिमिटेड इंफॉर्मेशन में हमारी कोशिश होती है कि हमको ज्यादा से ज्यादा इंफॉर्मेशन मिल जाए। तो फिर अब let's talk a little bit about this Zwicky transient facility. It uses a 1.2 meter telescope. It has 47 square degrees field of view. So field of view is an important number that you understand to see how much of the sky that you can look at. The area, the angular surface area of the moon or the sun as seen on Earth is about a 1/4 square degree. And what I'm saying is that with ZTF, we can look at 47 square degrees. So 47 divided by 0.25 is roughly 200. So 200 full moons fit in one image that we take. So it's a fairly large part of the sky, and we use different filters. So we can do 20,000 square degrees every 2 nights. That's the northern sky. And that's how many times we can observe the sky again and again. And we have a very large number of observations. And it is these large number of observations that we want to use to look at all these variable sources. Now, what is all this got to do with the game that we're going to talk about? Just be patient for a little bit, because that's where we are coming to. So there is so much variety in the sky. If you look at the variability tree, there are different kinds of stars that are eclipsing each other, stars that are pulsating, stars that are rotating and so change brightness. So you have heard that there are sunspots. The sun, when it goes around itself, there are some times when you see big spots, not with your eyes, you need equipment for that. But when you're looking at the sun with spots, it has slightly lower temperature there. And there are other stars which have much bigger spots. So when they rotate, you can see the lower temperature area, which means that the brightness goes down and so on. So there is a huge variety in variability of stars. And that is what we are trying to capture. And so with ZTF, what we do is that we look for these changes in brightness every night. Every night we find hundreds of thousands of objects which are changing in brightness. And then what we do is that we post these alerts for anyone who's listening. So it is mostly other astronomers who are listening to that. So what you see here are 3 cutouts, 3 images of the object. This image is what we took very recently, whenever this was taken. This is a reference image, which is a deeper image. If you were to take very long observation of the sky, this is what you would see. And this is difference between them, subtraction. And the subtraction, we see this bright object, which means that recently this object has been seen. It was not seen here. Look, this object and this object are the same, but this object, there's nothing that corresponds to here. And that's why when you subtract this reference image from the new image, you get this bright spot, which corresponds to this transient. And what you see here is the time series. On the x-axis is time, and on the y-axis is the brightness. So you suddenly see that the brightness of this object has increased. And that is what we are looking after.
So mix sir.
And so what you get, that's what brings us to Zard. कुछ लोगों ने म्यूट नहीं कर रखा है, प्लीज म्यूट कीजिए. So that is what brings us to Zard. Z-A-R-T-H, that's an acronym really. So the Z in Zard stands for ZTF. The AR stands for augmentative reality. That is reality that you can superimpose on things that are around you. And transient hunter is a hunter of transients. तो ये ZART जो है एक्रोनिम बना हुआ है. पहला Z जो है हमारे सर्वे का है ZTF का, दूसरा AR है ऑगमेंटेटिव रियलिटी का, ताकि हम हमारी खुद की दुनिया और ये जादुई दुनिया इकट्ठा कैसे कर पाते हैं उस बारे में है. और ट्रांजिएंट हंटर मतलब हम जो ट्रांजिएंट्स हमको जो मिलते हैं, जो ब्राइटनेस बदलने वाले अवकाशीय स्रोत, उनको कैसे पकड़ना, जैसे पोकेमॉन गो जैसा. इसीलिए कहा है क्योंकि हम ये ट्रांजिएंट सोर्सेस इस गेम में डालते हैं और आप लोग पकड़ पाओगे. और ये जी जो है ZTF वाला, ज़्विकी ट्रांजिएंट फैसिलिटी. तो हर रोज रात को जब ZTF नए सोर्सेस ढूंढता है तो उसमें कि कोई 50 से 200 तक हम इस गेम में डालते हैं ताकि आप लोग पकड़ सकें. तो देखते हैं. तो ये पोकेमॉन गो जैसा है, क्योंकि पोकेमॉन काफी टाइप के होते हैं. डार्क पोकेमॉन होते हैं, आइस पोकेमॉन होते हैं, वाटर पोकेमॉन होते हैं, कई किस्म के होते हैं, उनमें वैरायटी होती है. वैसे ही ये स्टार्स है. Just there is a variety in the stars, just like there is a variety in Pokemon, and that is how we thought about this idea of making Zard like Pokemon Go. So there were 3 undergraduate students who were primarily responsible for making this app. You can see their photographs there. And there were many others who helped look at alpha and beta testing and so on. So we'll be looking at more the app itself now. Okay, so now we are coming to the game. So maybe this is the time when what we can do is that if you have not already done that, we can do this together. So if you open your apps on the main screen, you have a login screen. So very likely you have already gone there. Then you choose a login name. There shouldn't be any spaces. It should be in Roman. And then you give permissions. It may want to store some of the cutouts that you have. There's no personal data that is stored. We do not store any personal data. And the name need not be a real name. So you can use a name that you make up. तो अगर सब लोग लॉगिन पे गए और अपने अपना लॉगिन कर लिए, शायद ग्रुप्स में हो सकता है, 3-4 के ग्रुप्स में हो सकता है, या फिर जिनके पास अपने पास टैबलेट है वो टैबलेट पे चले जा सकते हैं, एंड्रॉइड या टैबलेट दोनों में. तो zaarth.caltech.edu या फिर प्ले स्टोर पे zaarth पे चले जाते हो तो वहां से आप जा पाओगे यहाँ पे. So can I see if most people are there with us and they have gone in? Yeah, is there a way for us to check? Maybe people can just give a thumbs up in their Zoom or some such thing. So anyway, when you start
the students who have got the tablet and the Zaarth app with you can maybe raise their hand. We can all see you.
Hi.
Yeah, we have JNV Champawat here, sir.
Okay, so there are a few people. Good.
There are a few
so
people,
when you go in first, what you see is this screen, which tells you what are the kinds of sources that we have. There are 4 kinds of sources, 4 kinds of main sources that we have: hosted, orphan, nuclear, and variable. What does this mean? Hosted means that it could be a supernova because this star is in or near a galaxy. And a supernova is a star that dies. So it explodes, it becomes really bright, and then slowly it fades away. Then a nuclear source is also a source that is associated with a galaxy, but it's closer to the center of the galaxy. So it could be a TDE, for instance, the tidal disruption event, the star that comes really close to the black hole and gets ripped apart. Or it could be an active galactic nucleus, the other thing that we saw about the quasars or blazars, etc. And variables are those pulsating variables or binary stars that change in brightness. So these are the 4 main kinds. And then there are 2 more types. These are wild types or the ambiguous sources. So how do you know what kind of source is? The light curve that you see, we classify it using machine learning. And sometimes our machine learning classifiers, the classifier that claims something to be a hosted may say, oh, this is a hosted type. And we have another classifier which is looking for nuclear type. It may say, oh, this is a nuclear type. And so when we have 2 classifiers that are fighting with each other, both trying to claim the same object, we call it a wild type. So there are 2 wild types that are also introduced in Zaarth. And so even if you see this for the first time when you come in, there are menus within Zaarth which will allow you to see those again. So for instance, this ... you see at the top right, if you click there, you're going to be able to see this menu here. And when you click on different parts of the menu, the guide will take you back to this. Again, if you are not finding a transient, what you do is you click T in this, you click on the lens symbol, and then what comes about, if you type a T there and then hit return, then it's going to take you to a nearby transient. So what I'm going to do is that I'm going to start my phone and show you on this. You may not see it well, which is all right, but I've started Zaarth here. And then the main thing to do is that as I look in different parts of the sky, move my phone around, I see that part of the sky. That is the important part. So even with or without Zaarth, what you can do is that, and you don't have to be outside. You can do it from inside a room. It doesn't matter if there are walls and roof on top of you. And that is what the advantage of augmentative reality is. So we have put our reality on this phone. So it doesn't care whether there's a roof or not. When you point it in the sky, it's going to show you the sky that's exactly there. So if you know where the moon is right now, it's morning, so you may not see the moon right now. But moon is not seen only at night, by the way. I think it was close to new moon, so you may not see it right now. But if you know where the sun is and you're inside the classroom, and if you point your phone in that direction, you'll actually see the sun there. The main important thing, again, is that we get to learn about the sky through this app. And then within the app, if you touch the middle part, then you see a few menus there. And so the right screen is what is showing some of those menus. So the bottommost icon here, that of a telescope, that is the one that toggles the transients from ZTF. And the ones that are at the bottom show you which kinds of transients there are today. It shows leaderboards, etc. But these are the things that you should explore. You should touch each of those at different times and see what they bring up, what they're telling you. And again, pressing on the screen is going to get rid of them, or there will be a close button there. So it will be pretty intuitive. It will be pretty easy to look at. So this is related to the main screen. You log in, you create a name, and then you look at the guide and you understand what those are. And the main thing is that as you move around, and as you go around the phone, when you go around the sky with the phone, you can see these different symbols. And when you see one of them, you touch it. And when you touch it, then some information about it will pop up. And that's what we'll see on the next screen. Okay. So then what happens is that these are the kinds of things that you will see. These are specific types of objects as was described there. So this is a variable here. One is a nuclear, one is a supernova, etc. And when you touch one of them, this is the window that comes up. So in this window, it tells you what is the magnitude of that object. That is, what is its brightness. Then what is its nature, hosted or nuclear, etc. And then there is something called cost, something called points. And then there's the catch button. So when you catch the object, when you touch it again, this catch button, then it is going to get added to your list of sources that you've got. And 75 points will be deducted from your whatever you have access to, the credits. Every day you get a credit of 2,000 points. And then different sources, different objects have a different cost and different number of points. And one of the inner things of the game is for you to figure out what is what. So which objects have fewer points, which objects have more points, you can figure that out because there is some important astronomy in that. And then the other thing that happens is that if you click on more info, you see the more info there. If you see the more info there, you get to see more metadata of the object as well. So for instance, this pop-up comes up. Here you can see the light curve of the object. This is x-axis is again time and y-axis is brightness. So this shows, for instance, that the source was getting brighter and brighter and brighter. And if you see the x-axis, it's 1500 days, that is 5 years. So 5 years, this was getting brighter and brighter. And again, like before, there are cutouts here, but you see something else here, the RAN deck that shows the position of the object on the sky. And this cost is only 5, but you get 140 points. This also shows what the rarity of the object is, how rare it is. Again, the variable is shown here. And TNS, that's a number that shows how many spectra have been taken. A spectrum is the distribution of light through a prism. And then that tells you that what are the lines in that, because different stars, if it's a cold line, then cold star, it's going to have different metals. If it's a hot star, it's going to have different elements. So those elements we come to know about spectra. But the most important thing is that taking spectra is expensive. So we cannot take spectra of everything. And astronomers take spectra of objects which they think are interesting. And so if this TNS number is more than 0, it means it's more interesting. So you may want to catch more of those. And once you start catching objects, you get entered in this leaderboard. So for each type of object you see, your name will be entered in the leaderboard. Plus here you have this sharing mechanism, the standard sharing symbol that you have, which you can use to share it on the web or with your friends through WhatsApp and so on. You don't have to share it on the web. If you do that, that'll be great because more people know about it, because that is how we learn from each other, understand what different kinds of things are. So what is the purpose of this game? You get to catch, you get to have fun, but also you learn about the light curves of this object. So how do the light curves of nuclear objects change from compared to the light curves of hosted objects, or compared to variable objects, or within variable, which one of them are like Cepheids or Lyrae or different subtypes of stars? That is what you can understand by playing this game and understanding those. So one of the things that could be done, for instance, internally to a classroom, there can be a competition that the teachers can hold. Friendly competitions, because you can be in groups of 3s and 4s, and then you can bring them together to do lots of things. And what we have been doing is that we are keeping tally of all the leaders. but we also keep tally of weekly leaders. So every Friday at 0 UTC, when new sources are put in, the weekly leaderboards are also reset and new leaderboards start. So for a week, for instance, one classroom can have a competition among the students as to, let's learn this week about variable stars. So let's try to catch as many variable stars as possible. Every day there are new that come in. Catch about a dozen or so every day. But look minutely at how their light curves are different from each other. What is it that we can learn from that? Or how their cutouts are different? Or start with supernovae maybe. 1 week we learn about supernovae, the hosted sources, see how their brightness changes. So when you catch a transient, there's one more way, by the way. There is this button here, which shows like a finger. And if you click on it, then just with your hand, you can move the sky. I don't know if you can see it from there, because normally you cannot see it from the camera, but in case you are, you can move the sky around. And then when you see a certain variable, you click on it, and then you get a source. When you click on more info, you get another bigger thing, and then you get to see how the light curve is. And then you can use this other button. If you wanted to share it, you can share it different ways. Or this is the button to catch, so it's catching it, and it will get added to the leaderboard. And at the top right, you also see the streak, how many days consecutively you have been catching. And those 2,000 points, you have them for 1 day. The next day at 0 UTC, which is 5 p.m. in the US, but 5:30 a.m. in India currently, it gets reset. So every morning you wake up, you get new fresh credits. You can use it during the day until the next morning, and then you'll get more credits. And then you can keep catching these different objects. Again, these different menu items, you should explore them by looking at those. And then the main thing would be doing local collaborations and competitions. So learning about light curves of different types. As I said, 1 type per week. You can reason about ambiguous sources. There are also badges that are coming soon. We'll be adding, these are all gamification elements. So we add how many types of transients a given name, a given person has caught. So you'll see those badges when you go to your profile. And then the main thing about this app is for you to understand what these different kinds of astronomical sources are, share it. Again, the very interesting thing is that we put fresh transients on it. Every night, what ZTF finds, those are the objects that are put there next day. So these are really fresh objects. And so, for instance, if someone has a small telescope, or if a school has a small telescope, then they could even follow some of the brightest of these objects. Not all of them, because some of them tend to be faint, but then you can contact some bigger telescopes, some bigger observatories, and see if there are specific objects of these that you may want to look at. So that is how my observing had started long back, for instance. I think I've spoken for about 35 minutes or so. And what we can do now is that we can take practical questions, because this was like a demo. And so we can discuss a little bit any questions that you may have, and I can try to answer those.
Thank you so much, sir. So there are a few questions that, I thought that I, on behalf of the entire students, would ask. First of all, it was around, a lot of students from a very young age do think of becoming an astronomer or a scientist. But then somehow, they kind of deviate, and many things come up. Probably they are discouraged. They don't know how to go about it. So how did you, how could you describe what led to your decision to pursue a career in astronomy, and how you explored your passion for this field?
Okay. So it'll come to that. I'll answer that. But because I wanted to see if there were any questions related to what I described just now, and if they don't have immediate questions, what will be useful, it can be a good follow-up activity. So if you can contact the different teachers and ask them if they had some questions, or if there were any bottlenecks in their accessing the app, then I can help them later on with that.
Sure, sir. So students, do we have any questions with regard to what sir has explained right now?
They can maybe put it in the chat and you can collect it or whatever. So let me go ahead and answer your question right now in that case.
Yeah.
So yeah, meaning when I was growing up in a small place. So during summer, we could see the night sky and it was very exciting. But also when I was in 9th grade, so roughly the same age as most of the students here, Halley's Comet was around. So it came by. And at the time, I got access to a small telescope. It had a diameter of only 2 inches, so really tiny telescope, right? But through that, I could look at the comet. It looked like a tiny cotton ball, nothing more than that. No tail, nothing, just a cotton ball. But that was still so exciting because you could not see it with the eye. And then I had read that it comes around every 76 years. And so we are able to see something that comes every 76 years. You're not seeing it with the eyes, but you point the telescope in the right direction and you can see it and you show it to others and they were overjoyed also. So I think that really interest in astronomy. And then to continue with what I did with my passion, I think continuing to learn about new things, continuing to find interesting things was of great interest. And the observatories are spread around at beautiful locations. So being able to go there, being able to observe from there, kept my interest alive. So.
Thank you for answering that, sir. Another question that we had was, the concept of sky survey altogether, and what are its practical applications?
Right. The main thing about this app is okay, so with sky surveys, what we can do is that we can look at large parts of the sky, and now we can look at them again and again. And I think that is very critical because that is how we can see what is changing. So with sporadic individual observations, you get a static observation. It's like a snapshot. When you do sky surveys, it's like getting a movie, a very slow movie, perhaps a time-lapse movie kind of thing, but nevertheless a movie which will show you how things are changing. And you can see that for populations of objects, not just a small number of objects. And that really helps us understand the things that we are trying to study.
Okay. Sir, and also we heard from your introduction that you have also been into machine learning methodology and you're trying to transfer it into medical field as well. So how could you elaborate your engagement in that? How exactly machine learning can be used as a methodology in medical applications such as cancer detection?
Right. So machine learning can be generally used where there is a lot of data available. And in astronomy, as I said, with sky surveys, we have been looking at the same part of the sky again and again, large number of times. That allows you to gather a lot of data. So you can create training sets and train a machine to identify certain patterns. And then when you show it data that it has not seen before, it compares it with the patterns that it has been shown and tells you, okay, this pattern looks like that, that pattern looks like that. And if you know the names of those patterns, then the machine tells you, okay, this is an RR Lyrae, this is a Blazar, this is a TD, and so on. That's how we do things. Now, the machine does not understand anything. When we have given it a training set, which consists of stars and given it labels of stars, it can do that. But if we give it instead images that contain tumors, some tumors are cancerous, some tumors are indolent, then it can learn about that as well. So what one needs to do is one needs to abstract the information that we have. There is a lot of effort that one needs to put in cleaning the data first, because the data have a lot of noise. When we take images, for instance, we need to remove the bias in our instrument. We need to flat field the data. So all that pre-processing has to be done. So machine learning is not straightforward in the sense that you take raw data and just give it to the machine and it will give answers to you. There's pre-processing involved. You finish the pre-processing, then give the data to the machine. And then what the machine does is that based on the patterns that you have taught it, it can learn about it. So I'm not a doctor, so I don't know enough about cancer. So I cannot do everything on my own. So we do have domain experts in the loop. We work with them. But we tell them how our methodology works, and then they help us to abstract the data that they have collected. And then when that abstracted data along with the labeled data sets is given, then the machines can classify those objects. So that's the correspondence between, say, astronomy data sets and cancer data sets. The methodology can be very similar.
All right. So we also have a few questions from our students. So I would just invite them. If Ms. Sandhya Joshi from class 12 from JB Nainital. So she had a question. If she could unmute and ask the question. Ms. Sandhya from class 12, JB Nainital.
Good morning, sir. My question is, what are the key academic subjects in which one should excel if we are aspiring to pursue a career in astronomy?
Okay, so astronomy is physical science having to do with the sky. And the two subjects that I will highlight would be mathematics and physics. So you need to have basic understanding of physics, and having a good grasp of mathematics is really going to help you progress in this field. So math and physics is what I would say. But at the same time, within astronomy, there are many subdisciplines, and there are some other areas. If you want to go after, there can be other areas that you may want to be better at.
I hope, Sandhya, your query was answered.
Thank you, sir.
Yeah. Next, we have Miss Anjali Kumari from class 12, JNB Faridabad. Anjali,
good morning, sir.
Hello.
Good morning, sir. My question is...
Go on.
Could you describe various branches of astronomy?
Yeah, so I can hear echo. Maybe people should mute themselves. Yeah. So astronomy, there are many different branches, especially these days with having observations from the sky and from the ground. So you got pure astronomy, which used to be observational, but no one is generally a pure astronomer these days. You need to use a little bit of theory. So there are theoreticians. There are also people who do a lot of simulations. So computational scientists, that is also a part of astronomy right now. And then there are people who build instruments, people who do chip designs for astronomy, different things that you can use, cameras that you can use to observe. So I would say these are the very broad ones: instrumentation, and then optical or other observational astronomer, theoretical observational, simulations, and computation, etc. And there is of course communication is also important in astronomy, because whatever has been learned, it also needs to be communicated properly. Scientists do that on their own, of course, but there can be professional communicators, teachers as well, who are important. So these are different branches that I can say.
Thank you, sir. We now have Miss Gargi Naikal from class 12, JNB Sangli. Gargi, if you could unmute yourself and ask your query.
Good morning, sir.
Gargi, sorry to interrupt. What you can do is, I believe your volume is high, is up right now in your classroom. So probably you can lower the volume, ask your question, and then mute yourself. And then you can increase the volume again. Yeah? Otherwise, we will have the echo.
What are the career options in astronomy in Caltech Institute for us?
Okay, so some of the career possibilities in astronomy, I already in some way answered in my previous question. So there, for instance, you can become a communicator. You can become an instrument builder in astronomy. Then what you can do is that you can have a lot of computational knowledge and use that for something like machine learning. You can also become a theoretician in astronomy. So all these are there. And for instance, the theoretician will be closely connected to the physics and math part that I mentioned earlier, whereas an instrumentation scientist would need something like mechanical and or electrical acumen. So engineers, students who are doing engineering in either mechanical or electrical would also go into instrumentation of astronomy. And computers, of course, I already mentioned that. So you can do a lot of those.
Sir, I think she was also asking what are the career options in Caltech University? Where
in Caltech specifically, okay. Yeah, sure. So Caltech is a very small university. It has about 1,000 undergraduate students and then about 1,000 graduate students and a few hundred postdocs. So it has most of the primary technical branches. And so Caltech does take students in astronomy, but also physics who go on to do related astronomy fields. So Caltech is also home to a big group in the gravitational wave observations. And so again, computational stuff, then various things related to instrumentation happen there, computation happen there. And yeah, I mean, Caltech is a small university, but again, it will take students in many different areas of astronomy. So whatever area of astronomy you are, and if you're good at in that area, then you can definitely apply.
Thank you, sir. I hope the students are encouraged to properly check up Caltech University and the options available there for them. Next, we have a question from Miss Kritika from Genvi Una, class 12 standard. Miss Kritika, if you could unmute yourself and put the question forward. Kritika,
thanks, sir. I would like to ask you that did you face any obstacles during your academic journey and how did you overcome them? Thank you.
Yeah, I think facing some kind of obstacles is not uncommon and different people feel them in different ways. So I mentioned a couple of them. When I was doing my master's and I wanted to attend a summer school at IUCAM, and I had heard about the summer school, and I was in Nagpur at the time. The summer school was in Pune. And so what I wanted was 2 recommendations from 2 of my professors. And so one professor heard about that. I was not even asking him about it. And he made an off-the-cuff remark that, no, people from there will not take students from here. That was a very negative remark. It was good that I ignored that. I went to 2 other professors who gave me recommendations and I was able to go there. But this is the kind of negativity that you may sometimes encounter. You should not listen to such negativity. Be positive in your outlook. Look for people who are positive around you and follow your dreams. I think that is what will take you to your dream. So that wasn't really an obstacle, but I wanted to mention that because of the negative connotation that was involved in that. When I was doing my master's and I wanted to, this was after that, after I had been already to summer school, that was in my first year, but then after second year, I wanted to apply for PhD programs at various places. But at that time, I fell severely ill. And even my master's final year exams I gave when I was very unwell. Thankfully, it went well. I could do that. But what that also meant is that I could not give entrance exams anywhere. So that was like a big obstacle because then I couldn't apply anywhere. So I had no invitation from anywhere because of that. But then again, based on the previous things that I had done, I was able to go to IUCAM. They invited me based on the summer school and visiting students program that I had attended at that time. And what that meant was that I could go finally. But again, that was definitely a big obstacle that I had faced because I'd not been able to give any exams and I wasn't sure how I can get back to the science that I wanted to do.
Thank you so much for sharing that, sir. I'm quite sure that might be that would be very inspiring for the students who are present here. Next, we have a question from Ms. Dharani Dive from JND Puducherry, class 12th grade student she is. Dharani Dive, if you are there, you can unmute yourself and put your question forward. Dharani Devi from JND Puducherry. Are you there?
Jyoti, I think they are facing the issue. They have posted in the chat box their question.
All right, ma'am. I'll just take it out. So, sir, the question is, what advice can you offer the students for effective time management?
For effective time management, okay. Yeah. So one thing that I would say is that you need to be able to connect different things to each other. So if you learn something in one class, that doesn't mean that it's going to be useful only in that class. And this particularly applies to mathematics and physics again. So if you learn a physics principle, then it is not useful only in the next physics class that you go to. It is useful everywhere in life. And if you start following these connectivity things, then you'll find that learning new things becomes very simple or simpler. So because you're now finding connections and you don't need to learn something as if it's completely new, because its basis is already there in something else that you have learned. So if you keep that in mind, then that's going to help you. The other thing that I would very highly recommend is to be critical thinker. So whenever you are told something, if you ask critically, why is that so? How is that so? Is it simply because someone is telling us? Is it simply because it's written in book? Or can I do the reasoning myself? Again, if you go back to the first principles and try to build that argument, why it is so, then what that is going to do is that is going to tell you, remind you of the basics that you have been learning, because everything is built on basics. So if you have your basics pakka strong, then you'll be able to do those connections more easily. And as you do those connections more easily, you'll find that you don't really need to do time management separately. It will happen automatically because you're learning things as if you already knew them partly and you're building on what you knew. But again, the critical thing is to ask questions. Ask questions not just to others, but ask questions to yourself. Ask, why is this so? I'm being told something, but is it really true? Can I prove it to myself? Can I go back to the basics that I know and build it back up to that level? And this is true in any and every subject. Keep thinking, keep asking questions, and be true to yourself. And you don't need to do separate time management at all. It will happen automatically.
Thank you so much, sir, for answering that. So there is a question from in the chat box from Ms. Shweta Gupta from class 12 JNV Darbhanga. The question is, she would like to know if two stars can collapse with each other. And if they could, how does it happen and what's the phenomenon called?
Right. Okay. So coalescence can happen. The binary stars that I explained earlier, where you see two stars going around each other, what can happen is that those stars can come closer and closer to each other and coalesce. And in fact, the gravitational wave observatories are looking for exactly that kind of thing for specific kinds of stars. For instance, there can be two neutron stars, stars that are made only of neutrons completely. They are really dense objects. And if they're going around each other, then what's going to happen is that the orbiting is going to get faster and faster, and they're going to collapse. And when it collapses, it's going to lead to gravitational waves. Now, gravitational waves are different from electromagnetic waves. So infrared, ultraviolet, optical, radio, X-ray, all these are different parts of electromagnetic spectrum. And so whether you have an X-ray observatory or an optical observatory, finally what you're looking at are photons. But with gravitational waves, what happens is that it is a completely different kind of emission that you see. And the LIGO observatories, for instance, what they're looking at are how a given object is changing its dimensions in response to these gravitational waves. That is what they're trying to detect. So these are the waves that get emitted in strong enough amount, in good enough amount that we can detect them here. Another possibility is a black hole and neutron star coalescing, or even two black holes coalescing. So both the black holes are invisible to us in the sense that they are not emitting light directly that we can see, but two of them can come close to each other and collapse. And then that can lead to a big gravitational wave also, which we can feel here. So we may not be able to see the black holes directly, but these ripples tell us that two black holes have come together. So if you look up LIGO on your internet, you'll be able to find the detections that it has done in this fashion.
Thank you, sir. Sir, we have Miss Anjali from JNV Guntur who would like to ask you a question. Anjali, if you could unmute yourself and put forward the question.
Thank you, ma'am. Good morning, sir. First of all, this is Anjali. Now I am going to ask a question that, sir, what is the most important feature of an astronomical telescope?
One feature of it. Okay, so there are many things that are quite important. First of all, if it's an optical telescope or electromagnetic telescope, it's collecting area. So the bigger the telescope is, the more photons it can collect. But there are a few other things. It also depends on where it is located. If, for instance, if there is a site where it rains all the time, then it's not going to be very useful, right? But assuming that it's at a good location, the other things that determine it, what are the filters that go with it, or what is the resolution that the telescope can have. It's not really the telescope itself that supports the resolution, it's the instruments that go with that. So you really have to think about the telescope and the instruments going together. So whether it has a spectroscope, whether it has infrared instruments, whether it has ultraviolet supporting systems, etc. So the size is the biggest thing, and then these attendant things with instrumentation, the location, and all that, and people who work there, of course, unless it's automated.
So we also have this very interesting question, I think, which many might be having in their mind. It is put forward by Hema Sundari from class 12 JNV Puducherry. She wants to know if there is any relation between astronomy and astrology.
Okay, so I alluded to this very primarily earlier when I said that long back, what humans could observe were planets moving on the background of stars. And at that time, we did not know much about the universe. And so people ascribed specific forces to these planets as if they affected our lives. But no, the planets do not affect our lives directly or individually. And so in that sense, astrology is not even a science. It's just based on what people call statistics, but they're not even statistics really. So it is something that it's superstition is what I would say, because now, so what I said earlier, right? People in the time management question that I was trying to answer, that people should understand the basics. They should ask themselves that can planets really affect us? How would they affect us? The students study that there are four fundamental forces. And of those four forces, nuclear force, weak force, strong force, they affect over only a short distance, not long distance. The only force that affects over a long distance is gravitational force. And gravitational force goes as inverse square law. So if you double the distance, the gravitational force goes down by a factor of 4. If you triple the distance, it goes down by a factor of 9. And these are the things that they should not leave in their classroom. They should take the knowledge that they learn in the classroom out in their lives, ask the questions to themselves. So if I have got a planet like Jupiter far away and big, but it's so far away that even if it is massive, the amount of gravitational force that it puts on us is really minuscule. It doesn't do anything. And so in that sense, astrology doesn't have anything. So for instance, tides on Earth are caused by sun and the moon. Moon is nearest and sun is really massive. But those tides are not caused individually on us. For instance, if I drink a lot of water when there is high tide, that doesn't mean that the water in my stomach is rising, right? Because it's only that the entire Earth is being affected. And again, remember that it's the moon and the sun, because of their proximity and the mass, that they're affecting Earth. Jupiter or Saturn do not cause tides on Earth or on the entire Earth. So they don't affect us individually either anyway. So that's the questions that they should ask themselves and be able to answer based on first principles.
Sir, we also have this question, what is the difference between cosmology and astronomy? And also they're curious on how to get a placement in ISRO or NASA if they want.
Okay. So astronomy traditionally is more about observational astronomy when you look at individual objects or a small set of objects and so on. Whereas cosmology is about the entire cosmos, about how things came into being, how things evolve on the longer time scale or on a very massive scale, etc. Whereas astronomy would be on a smaller sets, individual objects, etc. ISRO and NASA both are concerned with launches into space or taking data from space, like observatories like JWST or recently the Chandrayaan thing, or there's going to be Gaganyaan also. So those things are where ISRO does, but ISRO also looks at the Earth from the sky. So ISRO launches satellites which are looking at the Earth and doing various measurements, etc. It also does things in various X-ray bands. So again, what would be important is either instrumentation or very good grasp of physics and mathematics that is related now to either astronomy or related to launches, rocket science essentially. How rockets are launched, what are the fuels that are used in that, or if you want to do automation in rockets, what it is that could be done, understanding spherical trigonometry, those are the kinds of things that you may need. And once you get good knowledge of that, then there are ways in which you can apply to NASA as well as ISRO. But again, the important thing is that there are also internships available in many NASA places. So JPL, which is part of Caltech, is also a NASA center. And at JPL, for instance, there are hundreds of interns that come every summer. They don't even have to be US citizens. They get access to a small part of it. There is a specific project that they do. And then whatever project that they're doing, it doesn't even have to be very deep and critical astronomy or cosmology or any space science related thing. But whatever they are doing, if they're good at it, then someone spots them and there would be ways for them to get assimilated into different areas of these fields. And now NASA and ISRO, both of them have many collaborations as well. So there would be ways of going from one to the other also in the near future.
Sir, there is another question on Big Bang theory. If you could explain it or how true it is. Yeah.
Well, so the Big Bang theory essentially says that the way the universe came into existence was through a primordial event where space and time itself were created. There was almost nothing, and from that nothing, the expansion started through this Big Bang, and both space and time were created, and it kept on going. And there was an inflationary period before, and things slowed down a little bit. Then there was stars and galaxies were formed, etc. So as far as it being true or not true, the evidence that we have through various methods that we have been using points to the existence of Big Bang. So if you look at galaxies and measure their redshifts, we find that they seem to be going away from each other. And then what is done is that is what is extrapolated backward, and we see that they must have been together at one point. And so observational evidence using astronomy, cosmology, those do seem to point to saying that the Big Bang is the correct theory. We still don't know many details as to what happened before the Big Bang, for instance, or what happened right at the start, or exactly when it happened. So there are small errors that we have in our measurements, but that is how science works. So we do better and better experiments. We reduce our errors, make them smaller and smaller, and get to know the universe to more precise manner, in a more precise manner.
Thank you so much, sir, for explaining and answering all the queries that the students had. To be honest, there are a lot of questions still pouring in, but as we do not have time, and we also understand that it's quite late night over there as well, all the students whose query were not addressed can mail their questions to Vigyan Jyoti email ID, and we can forward it to sir later. Yes. So, sir, thanks once again for being so patient. I think students loved the session, hence all the questions that poured in, it was very evident. It's time to conclude the session, and now I would invite Ms. Jessley from American India Foundation to deliver the vote of thanks.
Thank you so much, Justy. Good morning, dignitaries, teachers, and students. I'm Jeslie from American India Foundation. I would like to extend our sincere thanks to all of you for being a part of this memorable occasion. First, I would like to express my deepest gratitude to our distinguished guest, Dr. Ashish Mahabal, sir. Thank you so much, sir, for this wonderful session. And at the same time, it was very interactive. Thank you once again, sir. Now I extend my gratitude to everyone who have worked behind this event, especially NVS and IBM. Thank you so much for your immense support. Thank you, Modi sir and Minu ma'am, for your presence and support. We would like to express our appreciation to the audience as your active participation and engagement have added a dynamic and lively atmosphere to this session. Thank you so much, teachers and students. Once again, thank you all for being a part of this great session. Thank you. Have a great day.
Thank you so much.
Thank you, sir.
Thank you so much. Thank you, sir.
Everyone.